Hi everyone, thank you for coming to my talk. My name is Autumn Winch, and over the summer I worked with my mentor, Svea Hernandez at Space Telescope, and our project was looking into the history of Bart's spiral galaxy NGC1313. So to start off as an introduction, NGC1313 exists around 4.25 megaparsecs away from our Milky Way. And it is a very mysterious galaxy. It is beautiful. It has these beautiful spiral arms. It is a late type galaxy as well. It is barred, and also it has a detached region in the southwest that gives it a very unique morphology. We were able to study 5 star clusters within NGC1313, 201, 439, 463, 503, and 505. We had to study clusters actually because individual stars would be much too faint at this high of a distance. So we then used theoretical isochrones as well as synthetic integrated light spectra for our studies. We then compared with our models with observational data taken from the X-shooter spectrograph, the Very Large Telescope in Chile. And through spectroscopy, we were able to calculate the chemical abundances of these clusters. This leads to information such as age and the location of the cluster, as well as an increased knowledge of its stellar evolution, such as the initial mass function and the star formation rates. We also covered a range in the UVB and VIS arm of the wavelengths. So now on to the elements and the photosphere. So let's start out looking at an individual star. So the star is filled with a burning and a very dense material. And as this happens, photons of all wavelengths are released. So we can also talk about the photosphere, which is a cooler outer layer of the atmosphere. It actually has the same, or at least a very similar chemical composition as the star itself. So if a photon of the exact wavelength is released and absorbed, we can see the absorption line and take note of what element that correlates to. So it is also actually very important that we take note of the radial velocity, which occurs actually because NGC1313 is moving away from us, which ends up shifting the absorption lines in these spectra. Why should we end up studying the chemistry of these stars, supernova and stars? So stars start out being very hydrogen rich. As the star heats up, the hydrogen turns to helium. This then lowers the temperature of the star. The core of our star actually ends up contracting. There's a conversion process, which includes stages of these alpha elements. So for very massive stars around over 10 solar masses. However, when the iron begins to form, energy is absorbed and the star cannot handle its own weight and end up collapsing. And then let's also talk about the other system where we have these very low mass stars. If it's in a binary system and at least one of the 2 stars is a white dwarf, it could end up dying in a type 1a supernovae, which happens once the white dwarf overreaches the Chandrasekhar limit. This could happen as the white dwarf would accrete matter from its companion, ended up taking in too much mass, and it would die as well. The difference, though, is that a core collapse supernovae releases alpha elements such as calcium, titanium, magnesium, oxygen, and silicon, while the type 1a supernovae releases iron peak elements such as manganese, chromium, scandium, and cobalt. So after this, the elements are released into the interstellar medium and new stars will form from their remnants. So by knowing the origins of these elements, we can learn more on the history of these galaxies. So studying star clusters of various ages gives us almost a snapshot of the galaxy at the point in which the cluster formed. On to isochrones. So I'll start off going over the Hertzsprung-Russell diagram, which over here gives us the temperature versus the luminosity, as well as the spectral class versus the magnitude. And we can see for our white dwarfs down here, the main sequence and the very giant stars up in the upper right. So for this project, we were mainly focused on these isochrones, which isochrones are special models of the HR diagram, in which stars of the same age are represented by each of these lines. So this blue line has stars of the same age as, and this orange line will have stars of 5,000 milliyears. And then, so we were able to calculate these theoretical isochrones to generate them using Padova software. And we had to input age as well as assumed as one stellar population, as well as metallicity parameters. So on to our analysis and our process. So our data came to us mostly in this form of a wavelength versus flux diagram. So after we produced these theoretical isochrones, we used the isochrones to extract information on the stars within the cluster. We're able to gather information such as luminosity, flux, effective temperature, radius, and more. We're then able to use this information to compute atmospheric models, where we used software such as Atlas 9 or MARCS, depending on the temperature of the star. We were then able to create synthetic integrated light spectra, as you can see in this plot over here, where we have the absorption lines as the dips. Also note that we did not pay attention to the emission lines, as the emission lines do not tell us about the star's chemical composition, but rather of the elements that exist between the star and the instrument measuring. So over here we have our model is in the red, and then we compared our model to the extruder observations pictured in black. And so here's like the big part is when we actually use the code to find metallicities of our models, and as well as the metallicities, as well as estimates of the resolution of our extruder observations. We matched the resolution of the extruder data to our models. We were able to do this by applying a smoothing constant. The smoothing constant is used to derive the line of sight velocity dispersion of our stars. The constant held information both on the velocity dispersion as well as the resolution of our instrument used, which in this case was extruder. Talking about the metallicities, for each cluster, we found the overall stellar metallicities and are currently working on abundances of each of these individual elements. So generally, we can say that older stars have lower metallicities and younger stars have higher metallicities. Again, as the stars start out being very hydrogen rich, and it will take time for these iron elements to form. So as time moves forward, more iron elements are being released into the interstellar medium. So newer stars are made from this very metal-rich gas. So this plot in the middle shows a trend that we observe in the Milky Way. The x-axis is the metallicity, while the y-axis compares alpha elements to the iron peak elements. If this horizontal line moves up or down, the initial mass function changes. If the knee moves left or right, the star formation rate changes. The flat line is from the halo region, while the slanted line is from the disk. So this figure here, also to the right, this shows us that the closer you get to the center of the galaxy, the higher your metallicity is. So what else can we learn from this? If we have two star clusters of the same age, we would expect a very similar chemical composition. But if we end up getting something different, that is an indication to start thinking, is it possible that there is an inflow or outflow of matter into the galaxy? And then let's talk about when galaxies collide. So in the introduction, I mentioned that NGC1313 has a very unique appearance. It actually has a detached region in the southwest that does not seem to be a part of the bar or the spiral arms of the galaxy. And it actually turns out that the southwest experienced a significant increase in star formation. The galaxy NGC1313 appears to be all alone, but it is actually possible that it once had a companion. The displaced southwest region could be remains of our galaxy satellite. It was likely small as only that small region was affected. We were able to look at cluster 379, which lives in the southwest, shown by this red arrow. And we actually looked at a previous paper by Silva, which studies the cluster using band imaging, and their results indicate a possibility of collision. And the star formation rate increased rapidly just for this region, where the part with the bar in the arms had a consistent, there was a peak within the last 100 million years, which indicates the possible merge. So at these chemical abundances, we can look at this plot we made and see that cluster 379 is a bit lower than what we'd have expected. This is a good indication to maybe study these possible causes further. So after this, we hope to learn more about NGC1313 by continuing our studies. It is a great object to research. It has stars from a wide range of ages that could teach us a lot about development of galaxies and astronomical events. So thank you everyone for listening. Thank you to everyone at NAC, Lindell, Tiara. Thank you very much to my mentor, Svea. Hi. But this was a great experience. It was my first year, but I am extremely grateful to be part of this group. It's a great experience, and I hope the future has lots of many other great experiences for us. Thank you.
All right, thank you so much, Autumn. That was a great talk. We have time for a really quick question before we have to move on. From Andrew Baker, did you measure similar velocity dispersions for all of the clusters?
I believe we had I think it was more of a trend, I think, rather than the exact same. I don't want to say the wrong thing. Maybe I know Svea's here. I don't want to give you the wrong information, but I believe it was pretty consistent with our prediction.
You got it.
Great. Okay, great.
Hi. Yeah, so for the velocities dispersions of the clusters themselves, they were more or less very similar, between 4 kilometers per second, maybe 6-7 kilometers per second. So more or less what we would have expected for this massive star cluster.
All right, thank you. And so let's give Autumn a round of applause again as we move on.